Today instead we're going to talk about exponentials. So there are really two kinds of graphs that people get confused a lot. One is something that looks like y equals x to some number like 2. This is called a power model. And the other kind is something that looks like y equals 2 to the x. This is called an exponential. And you'll notice that in the exponentials, the number is the base and the variable is the exponent. And in the power models, the variable is the base and the number is the exponent. And we're going to be focusing on the latter, not the former. And pretty much all of these things look exactly the same whenever you work with an exponential. The differences are that the base will change the rate of increase a little bit if you have a bigger base. But in general, they pretty much are all the same. So, for example, if I'm looking at this particular exponential down here, 2 to the x, it looks like the following. And pretty much every exponential, for the most part, unless you alter it, looks like that. And then they have some questions associated with that. First one is domain. Remember, domain is pertaining to the x values. And as you can see, there aren't any really restrictions. So I could just say, if I'm using interval notation, negative infinity to infinity. However, the range deals with the y values, and as you can see, there's nothing below the x-axis. And that's because my range goes from 0, not inclusive, it never hits 0, and can go forever up. So positive y values keeps on going up. You can see the arrow on the graph. The y-intercept, or in other words, where does it cross the y-axis? Unless you've altered your exponential, you will always cross the y-axis at 1. That's because when you take any number and raise it to the 0 power, you get 1. So that's your y-intercept. 0, 1. Notice how the domains and ranges look similar to the y-intercept because the y-intercept's an ordered pair. Don't forget, domains and ranges, domains are only talking about x values. The ranges are only talking about y values. And the intercept is talking about an x, y coordinate. Okay, so there's a difference between what these things are referring to. The horizontal asymptote is the line that you shouldn't cross, but you can get really, really close to. So they're talking about this right here. It's actually the x-axis. If we were writing that down as an equation, we would say that the horizontal asymptote is y equals 0. And there's not really anything additional here that I want to talk about, so you can ignore that. The picture that you see here that has 2 to the x could work for 7 to the x, 12 to the x, anything like that. So in general, these exponential graphs look like this. Doesn't matter what the base is for the most part. There are some exceptions, but as a general rule, this is what the graphs look like. Questions? What's different about this second example? Negative exponent. So now if you look at the negative exponent, look what happens to the graph. What happened?
Flip-flop.
It reflected, because that's a good math word, over the y-axis. So the domain is still negative infinity to infinity. The range is still 0 to infinity. The intercept, again, is 0, 1, amazingly enough. And the horizontal asymptote is still y equals 0. But it is a different graph, because it has been reflected. So be aware, in the exponent, if you take the opposite, it'll be reflected over the y-axis. You probably should write a note. The negative reflects graph over y-axis. Number 3. In number 3, there are 3 graphs. let's look at the first one. Here's the first one. So the 4 to the x we talked about earlier, any exponential kind of looks the same. Looks something like this. Zero, 1. What happens if I change the exponent to x plus 2? Joe?
The y it's just higher up on the graph.
Okay, so it will be higher up on the graph. Why is the y-intercept higher on the graph? I'm looking for something a little bit more.
Because it starts at when y equals or x equals 0.
Yep.
You already have a 2 where the exponent would be.
Yep.
So then it wouldn't start out at 0, 1 because the 4 is already.
This x plus 2 thing right here tells me that the whole graph went left 2. Now, as a result, you have to be careful because that means something more than we think. So this graph now is crossing, and mine is not to scale. And Joe aptly pointed out that my new y-intercept is 0, 16. So when I shove in a 0, out pops 16 for the y value. So that has changed a little bit. So the blue graph has moved to the left 2 overall. That's what happened, shifted over. Now because it moved to the left 2, that means the y-intercept is going to be completely different because it's growing exponentially. Letter C. Letter C, I see the same thing that I had in B, which was different than A by a little bit. What has happened compared to letter A with letter C? 2 phrases, one at a time. Tristan.
Well, it's moving left 2.
Stop. Thank you. It went left 2. Right? And down 3. Excellent. Left 2 and down 3. So let's take a look at what happens. Let's say I find the y-intercept first again. So I know that I went to the left 2 because when I stick in a 0, I get 4 squared, which is 16. But 16 minus 3 is 13. So my y-intercept is right here at 0. Oh, I probably shouldn't have wrote that there. So I have my graph that went down 3. And this location is 0, 13. Now, of course, you can write down all other kinds of things that you want to, but this is kind of the main idea of what's happening. Our transformation rules work with exponentials. We talked about it with the absolute value graph. We talked about it with square roots, with quadratics. Now we're doing exponentials. These rules work with everything. So I moved it left 2 and down 3. This is my new resulting y-intercept. The graphs all still kind of look the same. The domain is still going to be negative infinity to infinity. The range is still going to be 0 to infinity. The intercepts now, though, are different. It was at y equals 0 for our asymptotes. So if you look at the blue and the red graphs, and we draw the asymptote, it was right on the x-axis, the y equals 0. But because the purple graph has been shifted down 3 units, the new asymptote for it would be y equals negative 3, which means actually that the range would go from negative 3 to infinity. So yes, when it's been shifted up or down, that changes where the asymptote is. Good job, Gannon and Liam. Okay, you may or may not know this, but a lot of people think the number pi is really important because we deal with circles, spheres, that kind of thing. And they found that actually there's a number that's probably even more important. It's called e. It's an irrational number, just like pi, which means it goes on forever, never repeats itself. And they found that exponential growth has a base of e in many, many cases. So like if you ever look at how bacteria grows, or money, or sometimes the petals on certain kinds of flowers, that kind of thing, how rabbits multiply maybe. It's an exponential growth model, and this E base is kind of important. And so in the table, they have all this stuff that you could type in your calculator and check out. I'll leave that for you to do on your own if you're interested. That's this stuff right here. So if you want to see kind of how it operates, there's a table you can shove in to your y equals and take a look and see what happens as your x turns into infinity with the y value. And you find out that it's 2.718 roughly. So as you go along, if you're looking for what this e value is, there's actually a couple of buttons associated with e on your calculator. This e is roughly 2.718. So we use 3.14 for pi oftentimes, and 2.718 is e. So pi is a little bit more than 3, e is a little bit less than 3. It's an irrational number though. Notice how this e, we said was a number like 2.17. It's a constant, a number like 2, like 3, like 7, whatever. So when I graph it, it looks just like any of the other exponentials. Has a y-intercept of 0, 1. It has a range that goes from 0 to infinity in the y direction. The domain, there aren't any restrictions. I can put anything I want in there. That's why it's negative infinity to infinity. And if I'm looking for the asymptote, I know that it's going to be y equals 0, just like my other exponentials. So e, even though it's an irrational number, acts like any other constant base for your exponential. Now, a long time ago, in medieval Europe, maybe around the world, people used to pay for things with certain kinds of metals. So you'd have like gold, or silver, copper, or something, and they'd have these round coins, and they'd call a quarter 2 bits or something like that, because you break off pieces of the coin and have 2 pieces to make 50 cents or a quarter or whatever it was that they made. And people weren't very trusting of other people, so they'd hide their money. And then later on, when things became more modern, banks developed. Safe places to keep your money. And so you give your money to a bank to keep it safe so that maybe you couldn't get robbed, that kind of thing. But people started to get wise to that, and they're like, wait, why should I give you my money? I mean, there are things I could use that for. So banks started to say, okay, well, we'll pay you to hold on to your money. And then what the banks would do is they'd make other business ventures and they'd make money off of that. And they'd pay you something to keep your money. That was called interest. And so a long time ago, maybe 100 years ago, there weren't very many people, so it was very easy to say, oh, Sarah, here's some money that you loan me, and I'm going to give you 5% of that back at the end of the year. And once a year, I'd settle up accounts with Sarah, and if she put $100 in, I'd give her $5 for letting me borrow her money for a year. And then at the end, she'd have $105. Now with the modern advent of technology, they don't do it that way anymore. What they do is they compound your money usually continuously. Sometimes they don't do it continuously. We'll talk about that too. And there are a couple of different ways to look at your money when you do that. So one is continuously, and one's not continuously. If you're not doing something continuously, then you're going to use this formula. So that's not continuous. If you are continuous, then you're going to use this formula. I call it the PERT formula because it looks like PERT, P-E to the R-T. And in this page, in this slide, you will see that they talk about what each of the different letters mean. For example, A is the amount that you get out of your account after so much time. P is the principal. That means how much money you invested. R is the annual interest rate. And N is the number of pay periods per year. A quarterly. That means if I say that was 12 daily, 5 on a non-leap year, and so forth. So let's try a few problems here and see what happens when we check these. So down below it says, I'm going to invest some money. I'm going to invest $5,000. What does the $5,000 represent? P. It's in an account that pays 6% annual interest, which represents R. And I'm going to go for 10 years, which represents T.